the next thing that we are going to go over is going to be the different OSPF LSA types. Now, before I can talk about the LSA types, I believe I owe you an explanation of what actually link state is. So we call OSPF a link state protocol, but what is the link state? What do we mean when we say the link state? Well, the link state is really a couple of things. One is it's the description of the link in terms of cost and type. So here we have some metric that is associated or type, and as I said, in the database this can be described as stub link, point-to-point link, or transit link. So there are only 3 network types that are inside the database. And also another thing that link state actually is relationships with other routers on the link. So when we say the link state, this is what we mean. This is the information that OSPF routers will have in their databases about every single link, every single interface in the network, in their area. So when we talk about different LSA types, this is what we have to keep in mind. What parts of this will be contained in that LSA type? So let's start with the easy ones. So we have type number 1, which is also called the router LSA. Now, router LSA is generated by all OSPF routers, and the data contained there, the important pieces of information, are the router IDs, router link states, I'm going to say router links. So this is the important information that is contained inside this LSA. Now, this field here is incredibly important. What is the flooding scope of type 1 LSA? Now, what do I mean by flooding scope? So flooding scope is how far in the network can our LSA travel unchanged. So when I have, for example, routers that are interconnected like this, how far in our network will this LSA, let's say, generated by this router here, so there is some LSA type 1, actually there is LSA type 1 generated by this router 1, how far in this network will it travel? Now that depends on how many areas we have. If this was one area, for example, the flooding scope of this LSA would be this, so this would be one area. But let's say that this here is another area. I may not be doing this correctly, so let me just so let's say that this here is another area. Now, LSA generated by this router here will have this as the flooding scope. And let's say that we have another area that actually sits here. And so this is LSA type 1 also, I do apologize. So this is LSA 1, but from router 2, this is router 3. So the flooding scope here for this LSA would be this area. Now, if this network was just a single area, if this was one area, the flooding scope of type 1 LSAs would be this whole thing. So this is what I mean by flooding scope. The flooding scope for type 1 LSAs is a single area. And let me clarify one more thing. What I mean by flooding scope is when this router generates the LSA, it inserts it in its local database. This means that this LSA identical must exist on this router and it must exist in its identical form on this router, because inside this area our databases must be identical. So none of these routers can actually change any information from that LSA. They can only send it as is, and this sending as is flooding. So I'm just going to send as is. This is what I mean by flooding. How far in the network will this LSA travel as is? So to give you a practical example, and this is the network that I'm going to use to examine all of the LSA. So I'm just going to draw 4 routers here. And let's say that this was R1, this was R2, this was R3, this was R4. Let's say that this is area 12, and this is area 0, and this is area 34. Let's say that that R1 here generates type 1 LSA. This is where this LSA is going to stop. So it is never going to leave the area in which it was generated. Now, R4 here may be generating its own, well, not actually maybe, it will be generating its type 1, and this is where this stops. Now, R2 may be generating its own type 1. So this is where this information stops. R3 is generating its own, and this is where it stops. Now, mind you, inside area 12, R2 is generating type 1 LSA, describing its own length in this area, and so does R3 in this area here. Now, important thing to note here is that on R2, there are 2 separate databases, and so are on R3. So the database here for area 0 is separate from the database in area 12, and here for area 34. So this is the green database, this is the red database. This is the red database, and this is the blue database. So these routers here have separate databases, which means that these routers, the border routers, will actually generate 2 type 1 LSAs. One in area 12 in case of R2, so this is R2 and this is R3. So this one here will be generating type 1 LSA in area 12 and in area 0, and R3 will be generating type 1 LSA in area 0 and in area 34. Area routers, like for example R1 and R4, are going to be generating only the LSAs for their own length in this area. Also, R2 here will be generating type 1 LSAs only for the links that exist in area 12. Those links that are in area 0 will not be sent in the blue domain, and these blue links will not be advertised in type 1 LSA in red domain. Now, one more thing that might be misleading here is router will only generate one type 1 LSA per area. Type 1 LSA contains, or may contain, I should say, information about multiple links. So, for example, R2 here may have 10 links in area 12, but it will still generate just a single type 1 LSA. And in this single type 1 LSA, we are going to have 10 link entries describing those 10 links in terms of cost and their relationship with other routers. Same thing for area 0 and same thing for area 34. Going back to our table here, let's take a look at another LSA type. This is LSA type 2. This one is called the network LSA, and it's generated by DR routers. Now, DR routers, as you remember, have two functions. The primary function is to create that virtual hub and spoke for exchanging the information on the local segment. And the secondary function is to let everyone else in the network know about this arrangement. And this is exactly this bit. Type 2 LSA is that secondary function. So DR routers on the segments are actually going to inject their information about the net mask and connected router IDs. So if we had a network that looks like this, so R1, R2, R3, when, let's say that this is our designated router, so here is where we have our adjacencies. Now R1 and R2 and R3 are both going to generate their type 1 LSA. And in this type 1 LSA, they're going to describe their local interfaces here. So the description on, let's say, R1 may say, this is, let's say, cost is, let's say, 100. And the designated router on the segment, and let's say that the IP address here is 192.168.1.3.1.3.2. And here we're going to have the information that the designated router is 192.168.1.2.3.3. The description of the interface, so this is in type 1 LSA. Type 1 LSA on R2, we'll have, let's say that the cost is 50. So the cost doesn't have to be the same, right? This could be a gigabit interface, or this could be a fast Ethernet interface, this could be a gig interface. So of course, sometimes the costs might be different. And we're going to have the information about the DR that is 192.168.1.2.3.3. This type 1 here is going to contain the information that, let's say, cost is, let's say, also 100, and that the DR is 192.168.1.2.3.3. Now, the important thing to note here is that every link state, every LSA in the database has an identifier. Now, the identifiers for type 1 LSA is actually going to be the router ID. So this is going to be R3, sorry. This is going to be R1, and here we're going to have that the link state ID here is R2, whatever that value might be. Now, because this router is the DR, it is actually going to generate a type 2 LSA as well. Now, the ID of this LSA is actually going to be 192.168.1.2.3.3. Now, take a look at this. All of these routers are actually listing the IP address of the designated router as the key to actually look up type 2 LSA. So they are telling other routers, if you need more information, look into this LSA. So the ID of type 2 LSA will actually be the IP address of the designated router on the segment. Information that is going to be contained in there is going to be the net mask, and connected routers. So in this case, we are going to have the list of R1, R2, and R3. Now, these are the router IDs, so whatever those values were, but the important bit here is the net mask, because inside these type 1 LSAs, there will be no information about the net mask, because this is the link type of transit. When you have the transit link, you are not specifying the net mask. The net mask needs to be looked up inside type 2 LSA that is going to be generated by the DR. So again, link type here is transit, and link type here is transit. So going back to our table, the information contained inside there is going to be the net mask and the connected router IDs. The flooding scope, just like with type 1 LSAs, is the area, because this information makes no sense outside the area. So technically speaking, if you remember my description of what LSA is, and it's the description of the link in terms of cost and type, and the relationship with other routers. We can see here that for the shared segment like this, the information about links is delivered individually by all the routers, but the actual relationships on the link are delivered by the DR only. So this is how we are actually optimizing the information exchange, because there is no point in this information being sent by all 3 routers, or 50 if we had 50 on the segment. So again, you see how the designers of OSPF actually thought this through, why this information here helps us out. So going back to our table, the next information, the next LSA type that we have is type 3, which is called summary LSA. And this is where some of the major confusions in OSPF begin. So again, I'm going to use the example of this network here, which is a perfect example for what I need. Let me just delete this a little bit. Okay. Now, let's say that we have a network N that exists here. So this network N lives in area 12. It will be advertised in area 12 as type 1 LSA and optionally type 2 LSA. So type 2 may or may not exist depending on what link type this was. If it was a point-to-point or stub, we won't have it. If it was broadcast or non-broadcast, we will have type 2. So this information ends here. Now, based on this information here, R2 is going to calculate what is the cost to reach N. Now, mind you, this was a simple network here. Maybe we had multiple devices here in between, right? So we don't know what's actually sitting in this network here, and it's borderline irrelevant, because what's going to happen, R2 is here based on this information here, and based on the costs of this link here and this link here, and whatever the path it needs to take, it's actually going to calculate the cost to reach N. So it's going to take the information from type 1, type 2, other information from the database, it's going to compute it, and it's going to generate a type 3 LSA, basically summarizing the LSA information, summarizing the database information, and it's going to inform the routers in area 0 that there is some network N reachable through R2 with cost X, the calculated cost X. Okay, so this is what we calculated, and this is the value that we are going to insert here. So basically we are saying this network, this cost to reach it. Now, this is what I was mentioning, that this is a very, very distance vector-like behavior. We have the route in a routing table, this is our cost to reach it, we are going to advertise this to our neighbors. Now, important thing to notice here is that the originating router of this information here is no longer R1, it is R2. So R2 generates this information. Now, R2 will be identified as the originating router for this LSA inside the database. And this originating router is going to be the router ID of R2. Now, R3 knows about R2 because it also had type 1 LSA describing R2 links. Now, what about R4? Can R4 reach the network N advertised by R1? Well, if R3 was to forward this information out, flood it out, we will have information here that this is reachable through R2, and R4 has no idea who R2 is because this information stops here. This is why the flooding scope of type 3 LSA is actually a single area. So this type 3 LSA stops here, but R3 is actually going to generate its own type 3 LSA. So it's going to look, okay, I have network N, so it's going to take this information here, and it's going to calculate its own table. Cost to reach N is cost to R2 plus X. Make sense? And let's say that this is Y. So this is the information that we have. So R3 is now going to generate a new type 3 LSA. And it's basically going to say that N is reachable through R3 with cost Y. Okay? As you can see, we are taking the route or information advertised by our neighbor, we are adding our own cost, and we are advertising this information out. Very, very distance vector like behavior. Now, when we have distance vector behavior, we always have problems with loops. So how do routers prevent loops in distance vector environments? Well, they use things like split horizon, they use things like count to infinity, etc. So let's take a look at how OSPF prevents loops in a multi-area scenario. Now, this is going to get very involved. And if you are hungry, please don't look at the screen now, because I'm going to start drawing some cookies. So let's say that I have 3 OSPF areas, or 3 network areas. Now, these 3 network areas, and of course, every time I need them to be separate, so apologies for that. I'm just going to do this one more time. So I have one area here. And let's say that inside this network, I have some relationships like this. So I'm going to take this and just clone it, and clone this one as well. So there are 2 ways these areas can be interconnected. Now, there is one way that is used by OSPF, and there is one way that is not used by OSPF. The way that is not used by OSPF would be this. In this scenario here, the routers are always members of areas, and links are the borders between areas. This is how ISIS works. But you don't care about ISIS, what you care about is OSPF. So the way OSPF works is that links are members of areas, but routers can actually be members of multiple areas. So what we need here are the routers that are going to be sitting between the areas, that have links that are members of individual areas, but they themselves may belong to multiple areas. So these routers here are called border routers, and border routers have multiple databases. So let's say that this here is area 1, this here is area 2, and this here is area 3. Now, even though I can't hear the sound from you, I see at least 1 or 2 you screaming at me, hey, but this is not how it works. You can't do this in OSPF. And my answer to that is, yes, I know. But bear with me, there is a reason why I'm doing it this way. So let's say that here, inside area 1, we have some network N. And we want to advertise this network to the rest of the network. So let's see what happens there. This route gets advertised inside this area as type 1 LSA. So this is an internal route inside this area. So remember, these routers here have 2 databases. Now, these border routers, and what I'm going to do here, I'm just going to observe information going this way. Of course, information might be going in the opposite direction as well, but bear with me. So let's say that this here is border router 1, this is border router 2, and this is border router 3. So border router 1 now has this information in its database, and it's going to create a summarized information, and it's going to inject it into this area here as type 3 LSA. So this information, as we know, is going to flow here, and this must flow to all these 3 routers and this router here, because the database must be identical. Now, this router here is going to create its own summary of this information, and it's going to inject it into this area here. So when this information gets injected into this area here, we create that information in the database here. So now this router 3 has this information in its database, and depending on the cost of these links here, it might actually inject it back into this area. So we get this information fed back and fed back here, which means that we need to inject it here, and we are running the danger of actually creating a loop in our network. Now, this would be the problem if there were no special safeguards against this in OSPF. But fortunately for us, there are actually safeguards to prevent this from happening. The first safeguard that we have, and let me go back just one page before because I wanted a clean copy of this diagram. The safeguards are that not all the routes in OSPF are the same. So the first thing that I'm going to say here is not all the routes are the same. OSPF divides routes in 3 categories: internal, inter-area, and external routes. Now, internal routes are those routes that are carried in type 1 and type 2 LSAs. These are type 3 LSAs, and these are type 5 and type 7 LSAs. I will talk about them in a moment. As I said, sometimes chicken and the egg. Now, how does this help with the problem that we had before? Well, the way it helps is that OSPF implements one of 2 possible routing philosophies. So let me just create a new slide here, and there are 2 routing philosophies as yours truly is concerned. One is so-called hamster routing, and mind you, these are my names. And the other one is hot potato routing. Now, why do I call it hamster routing? Maybe it's not this hamster routing. Maybe the more correct example would be squirrel routing. But I have this mental image. I don't know if you have seen Disney's cartoon called The Ice Age. And you know that tiny little squirrel that has that blinky eye and has that nut that it carries around the whole movie. And every time he sees that nut, he goes, "Eee, mine!" and keeps it. Now, that's what hamster routing is. Try to keep traffic as local as possible. Try to keep the traffic local. So OSPF is going to try to keep traffic inside an area as much as it can. Now, as opposed to that, hot potato routing is, for example, so this is done by OSPF. Hot potato, just to give you an idea what hot potato routing is get rid of it as soon as you can. And this is what, for example, BGP does. Now, if you remember, we haven't talked about BGP yet, but you probably know a little bit about it. BGP prefers external routes over internal routes. Now, the whole idea here is that if I have an external route and I have an internal route, assumption here is that this traffic at some point needs to leave my control. Now, I want to get rid of it as soon as I can, but why would I waste my own bandwidth? Why would I waste my own resources to send this traffic to an internal neighbor just to send it out of my network when I can get rid of it right here, right now? So that's hot potato routing. So OSPF actually implements what I like to call the hamster routing. It tries to keep traffic as local as possible. So how does that help with this here? Well, if we take a look at this, this is the order of preference given to routes. So this is preference. Internal routes. So if I have inside my network an internal route, I'm always going to, inside an area, give preference to keeping traffic local than sending it out. So this is going to be preference number 1, keep the traffic local, and only if I don't have the internal route, only then am I going to send it out of my area, and only if I don't have that, I will send the traffic outside of my autonomous system, outside my OSPF domain. So the route preference here helps just a little bit. How does it help? So going back to this complicated example that we had here, so let me clone this one. If we take a look at this example here, the reason why this situation here happened, why this information was injected, and the resulting traffic that might have actually followed this way and traffic looping is never going to happen. Because inside this area 1, we are always going to prefer these internal paths, no matter what the cost says outside. Because if we take a look at this network from the perspective of area 2 routers, of area 1 routers, this is how this network looks. Oops, that's not what I wanted. So I guess that I need to get just a little bit creative, so bear with me there. So this is the view, so this is our area 1. And the view of this network, so we have this border router here. Let's take a look at how this router sees this network. So this is the border, and this is the border here. So this router here knows about these borders, but it doesn't know anything about the network. There be dragons. The only thing it knows is that some networks are reachable somehow behind these borders, but it has a full visibility of inside the network. And it's the case of the devil I know is the better than the devil I don't know. So this is why OSPF tries to keep traffic locally here. Now, even though the metric here could say, hey, look, this metric is a little bit better, would you like candy? This is a problem, right? Because we don't know what is happening here. We don't know how true the information that is being fed here and injected by this ABR is, but we know exactly how good information inside the area is. So the OSPF is going to keep traffic locally. So this is going to prevent the actual traffic from looping. So this will not happen. We're never going to send the traffic outside the area only to receive it back. But it doesn't help us with this problem here when we had the actual routing information being injected from one area into the area from where the traffic originated. So this is where the second part of the solution comes into play. And the second part of the solution is, of course, something that most of you have probably been screaming about. And this is that this is not exactly how OSPF works. So my setup of these three areas, when they are interconnected as they are, is not possible. OSPF does not allow for that topology to be built. What OSPF requires is a dedicated backbone area that all other areas connect to. So this is a valid OSPF topology now. The one that we had before is invalid. So what we can have here is area 1, we can have here area 2, but this here needs to be the backbone area. Backbone area in OSPF, of course, is area 0. Technically speaking, it's area 0.0.0.0 because area IDs are also 32-bit numbers, but in iOS we can just call it area 0. Basically, what OSPF requires us to do here is to implement a hub and spoke at the area level. Now, if you have hub and spoke, can you actually have a loop in hub and spoke environment if you don't have spoke-to-spoke connectivity? You cannot. This is loop-free by a definition. So this is why we have area 0, why we have the backbone area. Because now this internal information that we have here in these routers, when it goes outside the area, when it's injected here, and when it's sent to this router, it will be injected into this area here, but there is no way that this information can find its way back. There is no way it can go back because we have a loop-free environment, inherently loop-free environment. But there is, of course, a problem with that, because this, what I'm going to do next, is also a perfectly legitimate OSPF topology. So bear with me until I clean this up a little bit. So now, let's say that on our area 2 here, instead of having just one border router, we have more than one border. So we are going to have, let's say, border 1 and border 2. This, or let's make it even more fun, like this. So this is 1, this is 2. So now, what we have here is a potential for the loop. So we had this internal information that was now injected into this area here. And eventually, both border 1 and border 2 in their green databases are going to learn this information. So now, let's say that border 1 injects this information, and this information now reaches border 2. Border 2 now should take this information and actually inject it back into the database, which means that eventually this information might find its way back. Now mind you, these routing information, these routes will never actually be used for routing, but you know what? They might populate the databases here. And this is a looped information. Not to mention that a similar thing may have happened in the other direction. R2 here, or border 2, may have injected this information back. So now we are going to get even more information in the database here, and this information makes its way back. So we somehow need to find a way to prevent the loops happening here. Because what we have now is really not a simple hub and spoke, but what we have now is a redundant hub and spoke environment. Now, when you have redundant hub and spoke environment, and let's say these are all the same interfaces, how do you prevent the loops? Well, you prevent the loops by taking the routes and preventing them from being advertised out of the same interface they are received on. So what we need to do here is implement a split horizon. So when people ask you, does OSPF implement split horizon? Of course, you're going to answer no, because at the interface level, OSPF does not implement split horizon. But at the area level, in order to prevent this problem from happening, we may need to do something that looks like a split horizon. So what can we actually do to address and fix this problem? So let's take a look at that. So I'm going to paste this in, and again, please bear with me until I clean it up just a little bit. Maybe I should really have more efficient copy-paste buffer than this. I'm efficient when it comes to configuring stuff, but when it comes to drawing stuff, I'm really not that good at it. So, what we need to do here is we need to prevent this information that is injected by this border 1 from ever leaving the area. So this is where this information needs to stop. Also, information injected by this router here needs to be prevented from leaving this area here. And OSPF does that. So on the border routers, what we are going to have is a split horizon rule. Type 3 received from area 0 will be summarized, and by that I mean new type 3 will be generated, into non-zero area. Information, or actually type 3 received from non-zero area will not be used for routing. That basically means that information that was injected here by R2 will be in database here, will be in database here, database here. It needs to be in the database on this router. It cannot reject it because the database must be in sync in the whole area, but this router will not use this information for routing. If it doesn't use it for routing, it cannot calculate the path for it. Why? Because if it's not in a routing table, there will be no calculated cost for it. If there is no calculated cost for it, that means that this route will never leave this area. Same thing happens with this information here. So this is the split horizon rule that OSPF implements and prevents the loops in a multi-area environment. This is very, very important because there will be situations that some router appears to be an ABR, but it actually is not an ABR. So let me give you that example. So let's say that we have a router, R1, that sits between two areas. The number of interfaces or neighborship in these areas is relevant. So let's say that this is area 1 and this is area 2. If you have this situation, this router in OSPF, in iOS, is not an ABR. Now, this router is not an ABR because it's connected to area 0 and area 2, which are non-backbone areas. There will be no summarization of information between these two areas. So this router will have a database in area 2 and will have database in area 1, but there will be no information exchange between these two areas because in iOS the routers cannot summarize between non-backbone areas. They can only summarize the LSA information between non-backbone and backbone area and between backbone area and the non-backbone area. So this direct summarization in iOS is not an ABR. Now I'm saying not in iOS because, for example, in Junos it is. So in Junos this router will be, for example, considered to be an ABR, but there are still caveats with this, and I'm just putting an asterisk there just so you know it. This is an iOS specific behavior. There is actually an RFC that is written what makes a router an ABR in different implementations of iOS, because RFC is rather vague on the subject of what makes an ABR. But in iOS, this is not an ABR. Which brings me to the next point. The next point here is, let's say that we had a network that looks, and I believe I already have that thing. So let me bring one of the older slides. Just have to find it. We've done so many in between, so that the one that I need might be a little bit lost. I will need to clean it up, so maybe I'll be just faster actually redrawing. Yeah, I will definitely be faster redrawing it. So R1, R2, R3, and then R4. And let's say here that this is area 1, that this is area 2, and that this is area 3. And let's say that we have a network N that exists here. We know that this will be advertised as type 1 LSA and will exist in database here. But because this is area 1 and this is area 2, there will be no summarization of this information going through, so no routers in area 2 can actually reach any networks from area 1. So this is a known thing. But what if, for example, this was area 0 and this was area 0? What is the situation there? Well, let's take a look. we know that this will information be sent as type 1 LSA. It will exist in this database here. This router now is an ABR, right? So this router here is an ABR, which means that this information will be actually summarized and sent to R3, which will now have this information in its database here. But take a look. This is a non-backbone area, and this was a type 3 LSA received in a non-backbone area. What is R3 going to do with it? It cannot use this information for anything, which means that these guys here in area 0 cannot reach the nodes, cannot reach the destinations in another area 0. So this here requires a fix. Now, the fix, of course, stems from another requirement in OSPF, and the requirement that we are failing to meet here is that area 0 must be contiguous area. That means that we must have an uninterrupted connections between area 0. We cannot have split brain like this. So this is supposed to be the exact same database here, but it is not, because this router here cannot inject the type 3 LSA from a non-backbone area back into the backbone area because of the split horizon rule. So how do we fix this? Well, the fix for this, well, there are multiple fixes. Somehow we need to extend area 0 across area 2. And one of the possible solutions is to use something called the virtual link. So what we might need to do here is, let me just use this. So what we might need to do here is the virtual link. Now, virtual link is IP unnumbered point-to-point link, which is always in area 0. So you cannot have a virtual link that is in a non-zero area. Now, this might sound confusing because the actual syntax for configuring virtual link is router OSPF, let's say 1, and then you say area, in our case, this was area 2, virtual link. And then you specify the router ID of the destination. So what am I saying that virtual link is always in area 0 when this one is in area 2? Well, area 2 in this case is something that we call the transit area. So we are telling our router, create the virtual link using area 2 as the transit area, but the actual virtual link, so let's say that we had R1 and then we had any number of routers here and we had R2. So let's say that this here was area 0, this was area 0, this is area 2. What we are basically telling our routers, in area 2, create this virtual connection between R1 and R2, but this virtual interface that gets created here and created here will actually be in area 0, creating one contiguous area 0, so that the database on this side here and the database on this side here can actually be in sync. So this is what the virtual links do. Now, another solution that you can use, and I'm not going to spend too much time on it, is that you can actually use GRE tunnel for the same purpose. Let me just be a little bit more pedantic about it. So you can use GRE tunnel about it as well. And with GRE tunnel, you are not restricted to actually being it unnumbered. You can put IP addresses on the interfaces. But if you decide to use the virtual link, this is what happens. Also, sometimes, especially in the CCIE lab environment, what you might encounter is the situation. So here I'm going to use a little bit more routers than just 4. Is that you have, for example, now this would be an extreme case, that you have area 0 here and area 0 here, but this is area 1, 2, and 3. Now, how do you interconnect these two area 0s? Well, if you want to use virtual links, what you actually need to do is you need to set up a cascade of virtual links. So you need a virtual link here. you would need a virtual link here. You would need a virtual link here. And then you would have native connectivity here and here inside area 0. But basically, what you will have is one contiguous area 0 in this case. Now, keep in mind that in any of these areas, so let me use this area as an example, you don't have to have a direct connection between these routers. You can have any number of routers in between, but you are always going to be building virtual link between ABRs. So this is an ABR and this is an ABR. You cannot cross multiple areas with virtual links, and the reason for that is that the destination of the virtual link is not an IP address, but it's a router ID. So this is very, very, very significant piece of information. One of the questions that I received is, when creating a virtual link between loopback interfaces of two routers, does one of them need to be in area 0? I'm going to repeat this again. The virtual links are built between router IDs. They are not built between the interfaces. So it doesn't matter in which area interface that borrowed the number to router ID resides, because the virtual link is not built between that interface and another interface. It's built between router IDs. So router ID is not an IP address. So if you want to build a virtual link between router R1 and router R2, and R1 has loopback interface in area 19, and that loopback address borrowed its IP address for router ID, that's irrelevant, because router ID exists in all areas, because router ID is unique per process, not per area. So the answer is no, you don't need to have loopback in area 0, because it's irrelevant. Another question was, if I have this cascading setup that I need to do, if I have these multiple areas, and if I wanted to build a GRE tunnel between, let's say, this ABR here and this ABR here, that would require no less work than using cascading virtual links. Well, that depends, because you see, for GRE tunnel to come up between this point and this point here, for GRE to come up, all you need is to have the route to an endpoint. So you can have static routes, you can have EIGRP routes, you can have any means, as long as this router somehow can ping this router here. Not necessarily through OSPF, but if you have some other ways of reaching it, you could actually build a GRE tunnel bypassing these two here, or bypassing area 2 complexity here. So with GRE tunnel, you are not necessarily bound to this cascading setup, but you would need to have some external ways of knowing the routes. But for virtual links, you cannot use these shortcuts. For virtual links, you actually have to do it between the ABRs, because again, virtual link endpoints are not IP addresses, they are router IDs. But for GREs, they are IP addresses, and if IP address is reachable, you don't care how, you can build the GRE tunnel, and then if you have the GRE tunnel, you can run OSPF over it, and you can actually interconnect these two areas. Another question is, if in a virtual link scenario, so unrelated to GRE, if I need to build the virtual links between the router IDs, do router IDs need to be routable? Again, they are not IP addresses. They are not routable, they are not pingable, not necessarily, but if you have valid adjacencies in one area, you can assume that from OSPF perspective, the OSPF will know how to reach that router ID. That said, this was actually an excellent question. Why is that? Because even if you have router IDs, so let's say that we have router here and we have router here, and we have something in between them, right? And what I want to do is I want to build a virtual link between these two routers. So these are the ABRs. So this is area 0 here, this is area 1, and this is area 0 here. Now, when I'm building this virtual link, what I'm configuring is router OSPF. Let's say that this is ABR 2 and this is ABR 1. So I'm going to say router OSPF 1, and I'm going to say area 1 virtual link, and let's say ABR2. Now what I'm entering here is the router ID. But you know what? The actual IP packet needs to be sent here. So what router ABR1 is going to do, when it sends the hello, so this is the hello that needs to be sent. So this is an actual IP packet. An IP packet must have the source IP address and must have the destination IP address. So what ABR1 needs to determine is which source IP address to use and which destination IP address to use. So the router ID itself is not an IP address, it's not routable, but we need to find at least one routable IP address inside this area on this router in order to be able to reach it, which can open a whole new set of problems if this here was, for example, IP unnumbered link. Now, if this was an IP unnumbered link that borrowed the IP address from another area, your virtual link here will never come up. In that case, what you need to do is you will probably need to build a GRE tunnel up to here, or maybe virtual link up to here, and then you would probably need to build a GRE tunnel here. And hoping that this here was a PPP link. Because if it was HDLC, it wouldn't work. But because if it was PPP, you could build a GRE tunnel, because in IPCP you will have that weird /32 for your neighbor. Now, there is a blog post, there is an article that I have written on this subject. You can find it on blog.ipexpert.com. It's OSPF and IP unnumbered links. It actually describes this scenario and why it's so complicated and complex. At this point, you may not remember that we have actually been working on some OSPF table, but let me remind you about that. So this is the table of our LSA types. Now, I went on a tangent explaining what type 3 is, how the OSPF works in an inter-area environment. So knowing all that stuff, type 3 LSAs are actually going to be generated by ABR routers or the area border routers. And the data contained will be summarized information contained in type 1 and optionally type 2 LSAs. So this is the information, let me summarize it, and let's see if I can fit this in one. Like so. Now, the flooding scope is going to be an area.